פועל? אוקיי. Okay, let's continue. So actually I was a bit inaccurate when I wrote this variance hypothesis because both VP and VNP depend on the field. Okay, so basically we should say probably, right, that over any field F, they are different, right? Okay, that's one thing. And the other thing is just, yes?
You know some examples when the field is different and it turns out that they look similar?
No. A field, you mean field or? No. So the permanent and the determinant, so if you walk over GF2, then permanent equals determinant because there's no minus ones. But in that case, permanent is not complete. But for other fields, it is. Right. And let me just state a theorem that assuming the generalized Riemann hypothesis, right, that's what I need. Yeah, so it implies, say, over the VP, over complex numbers, say. Okay, so this is the class of Boolean circuits, and this is the circuit analog of NP. I will not define those, but it's a non-uniform version of the P versus NP equation. And if you don't know what it is, I mean, intuitively it's like if P is different than NP. It's not the same question, but it's similar. Then, if you also assume GRH, then you get this. I'm not going to prove this. You can find it in Burgiser's book, Peter Burgiser's book. Okay, good. So that's one thing I wanted to say. And also wanted to mention another way to think about VNP, which maybe, it's not another way, it's some restriction of VNP, but it may be easy to work with. And I'll just give the intuitive definition, just maybe say something intuitive that a family Gn is in VNP if given say n and an exponent vector. What do I mean by that? For example, if E1 up to En is an exponent, or En is an exponent vector, so you should think about it as corresponding to the monomial Ex E1 up to Ex En. So I'm using the same letter N to denote everything that's polynomial in N, but I mean, just for the intuition's sake. Then, so we can compute the coefficient of the monomial, of this monomial in Gn in, say, sharp P. Okay? So, yeah, okay. For example, for the permanent, if I give you a monomial, you can easily check what is the coefficient, right? You just have to check whether the exponent vector defines a permutation. And if it does, then the coefficient is 1. If it doesn't, the coefficient is 0. So that's a very simple calculation. Okay? And actually, during the break, someone asked me whether, is it true that for every so is it true, so that's the question I was asked, is it true that if F is a small arithmetic circuit, then there is also a small circuit, or it's easy to compute each of its coefficients? So, and the answer to this is no. And the reason is the following, it's actually written on the board. But just look at the following example. Right? That's a polynomial from the computation of the permanent, right? Now, what is the coefficient of y1 up to yn? What does it mean? How do you get y1 up to yn? So think about yi's. Y1 multiplies the things on the first column, Y2 multiplies things on the second column, etc. So basically, to get that coefficient means that from every row you take one element, and from every column you take one element. So it's exactly the permanent. And we don't believe that the permanent has small circuits. We don't believe it's easy to compute or anything. So computing a coefficient, even of an easy polynomial, and this is like a trivial polynomial, right? It's difficult. Okay? Good. So just as a rule of thumb, if I give you a polynomial, you want to check whether it's in VNP or not, just see whether it's easy to define its coefficients. If it's easy to define its coefficients, it's in VNP. Right? And all the polynomials that we deal with will be, yes, I mean, certainly all the polynomials that I wrote on the board, like the symmetric polynomial, the determinant, the permanent, given a monomial, it's very easy to compute its coefficient. Okay. A coefficient, but there are exponentially many.
Yes, so why the determinant is in VNP, right? So
Determinant is in VP even.
permanent is in VNP.
Yes.
But you cannot compute.
I can compute a coefficient, but I need to sum all coefficients together, and there are exponentially many of them. That's the summation. I mean, in some sense, that's the summation in the definition.
Oh, you can compute in VNP and you say that.
No, but even if I can, if for the permanent, I have an efficient circuit to compute a coefficient given a monomial. But I cannot compute the value of the polynomial. Because I need to sum over all coefficients. There are exponentially many of them.
I understand, but you just said it's not general theorem that given a polynomial has a small circuit, we can compute its coefficient.
No, here is an example. That polynomial is a very small circuit. That's a circuit, right? And the coefficient is a permanent. The coefficient of this monomial is a permanent. I mean, maybe the permanent is easy, but that will be more interesting than, I don't know, yeah. Okay, good. So now I want to define the reductions that are being used. Okay. So the notion of a reduction in the algebraic world is called a projection. So what is a projection? So let's say that, okay, I want to say when does, I want to say that polynomial g of x, when is a projection of a polynomial, I don't know, f of y. Okay? So, okay, so when there exists, so there should be some map that does the following. What I want to do is to replace every variable of f with either a variable of g or with a field element. So there exists a mapping that takes the yi's and sends them to the xi's. Right? So to each variable, I assign either a new variable or a constant. Okay? And such that g of x equals f of rho of y1, rho of y. Say we have y1. Okay? So basically I mean, it's the simplest kind of reductions that exist, right? Think about it. If you had the circuit for f, let's say that f is a small arithmetic circuit, then how do you get a circuit for g? You basically relabel inputs, right? If an input was labeled with y1, you put rho of y1, which is either a variable or a field element. So it is clear that if f is easy and g projects to f, then g is easy. So it's almost the most trivial kind of reduction you can think. But it's also a powerful one because we have the following very nice theorem. And it's, yeah, HRF. Then, okay, let me just define it. Okay. So the theorem says that permanent is VNP complete. Again, you need the field to be different than characteristic 2 because then permanent equals the determinant because minus has no meaning. And then, and what is the P projection? I should have said it here. So if M is polynomial and it's P projection. So I should have been more accurate. I'm sorry. So what I should have said that we have a family of polynomials Gn, and the family of Gn projects to the family Fn if each Gi projects to some Fj when J is polynomial in I, and the number of variables grows at most polynomially, etc. Okay, so yeah, I mean, take this definition and make a correct one. Okay, and but yeah, okay. So basically, we should have maybe I'll use a different. So there should be a family Gn and a family Fn, and there is the row n such as Gn, and then polynomial also S. So it's S of n, and M is at most S of n. Okay, something like that, right? There's another family, so the n polynomial from here projects some polynomial there, and everything is polynomially, grows polynomially. So this theorem says that permanent is VNP complete. So in other words, whenever you can represent a family like this, when as a summation, when this is in VP, then you can also represent Gn as a projection of the permanent. Okay, so I will not show the proof of this theorem. It's a gadget reduction. It's very clever, but I mean, it's a bit technical to show, so just skip it. So there are other families that are VNP complete, natural families. So basically, that's also something perhaps I should have said earlier. So when I presented VNP here, I presented the, maybe I'll click that, as an analog of NP, where the OR is replaced by a summation. However, for those of you who have seen it, there's also the class of functions that is called Sharpie. So, right, so P and NP are classes of decision problems. Sharpie is a class of functions, and basically Sharpie, for every such L, you can define the function, maybe FL of x, which is the summation of y, of 1 LXY. So it counts for every x, how many witnesses it has. So it's now a function because it returns an integer. And this perhaps looks more similar to the definition of NP. So it's a class of function, and the permanent, that's maybe you've heard it also Violent proved it, is also complete for Sharpie. Okay? And basically, if you take any NP complete function, like 3-sat or Hamiltonian cycle, etc., and you define the functional version, right, of it, then you get a counting problem that is complete for Sharpie. And you can also define an analogous polynomial in VNP that will be complete under P reductions, but I'm not going to show that. Okay, so there's also a polynomial coming from Hamiltonian cycles that is VNP complete, etc. Okay. Yeah, the Hamiltonian cycle. Just permanent is just. Yeah. By the way, an interesting thing is that I said that usually to get a Sharpie complete problem, you have to start from an NP complete problem and take the counting version of it. The permanent, something unique about it is that it is a counting problem of a problem in P. What permanent counts, and think about it, I'm not going to show it, it's very simple to see if you have 5 minutes and some free time. Is that it counts the number of perfect matchings in a graph, in a bipartite graph. Just think about right, the rows presenting the left-hand side, the columns the right-hand side, and you put xij if there's an edge between I to j. So what is a diagonal? It's a matching. So the permanent counts the number of matchings, right? The permanent of a 0-1 matrix is the number of matchings. So permanent, and we know to compute, to decide matching in polynomial time, right? There are many simple algorithms for that. So something unique about the permanent that it's a counting version of an easy problem becomes sharply hard and VNP complete.
When you speak about computing the permanent in this context, do you mean over the integers, over the rational?
Yeah, I mean, I give you a graph, just output, yeah. Give me an integer. I mean, the rationals, I mean, whatever. But, yeah. I mean, pick your own field. No, GF2 is a determinant, so it's easy. Because there's no minus, right? Over GF2 is easy. Because it's like the determinant, because the minus 1 equals 1. Okay. Great. So, okay. So, great. So we've seen. I claimed that the permanent is VNPR. I'm not going to show it. But now, let me show if the determinant is also complete. Not exactly for VP, but something slightly different. So what I want to do next is let's define, okay, I'm not going to write all this definition accurately, but VQP, where Q does not stand for quantum dorit, it's Q is quasi. So it's like quasi-poly. What is a quasi-polynomial? So quasi-polynomial, poly, S is okay. S from n to n is quasi-poly if S of n, if there exists some C, some most, not totally, C of n. So it's a function that whose log is polylog in n. Okay? So it grows faster than any polynomial. I mean, if C is larger than 2. Or C is larger than 1, I guess. If C is larger than 1, it grows faster than any polynomial, but smaller than any exponential. Okay, so it's quasi-polynomial. Right. Yeah, because of our lack of ability to prove things, we also call this efficient. But, I mean, you can do whatever you can, right? Great. So that's quasi-poly. And you can define VQP, and you can define VQP in a very similar manner. Now, instead of bounding things by a polynomial, you can bound things by a quasi-polynomial, and etc. Right? So there's and then it's a theorem that is VQP complete. What do I mean by that? So if you have a family of polynomials that are computed in P or in VQP, right? So they have a quasi-polynomial size circuit. Then you can find the matrix, and you can actually compute that matrix very efficiently. And the matrix will be a quasi-poly by quasi-poly. And the determinant of that matrix will equal the output of the circuit. And this is something actually that we're going to prove today. Okay, we're going to show that determinant is VQP complete. But before I prove that, I want to state now Valiant's extended hypothesis. And that says that VQP is different than VNP. Or in other words, it says that permanent is not a quasi-polynomial projection. Again, you can define the same thing with quasi-polynomials, and now what will be the difference? This S will be quasi-polynomial rather than polynomial, so you allow, if the permanent is of n by n matrix, you allow the determinant to be of a quasi-polynomial, like n to the log square and by n to the log square n matrix or something of that. Okay? So again, so what does this say? That, or in other words, i.e., that if you want to represent term of x as that of y, where yij is in xij union f, Okay? So we want to represent the permanent as a projection of a determinant. Then the variant extended hypothesis says that the size of this matrix should be larger than quasi-polynomial. Okay? That's variance. Yes?
Do we have a separation theorem here? Is VQP not equal to VQ?
We don't know anything about anything. But I mean, okay, we do know some things about some things. Yeah, so we know that, for example, if you further restrict the computation and you consider what's known as multilinear model. Now, what is a multilinear model? So a multilinear polynomial is a polynomial in which, in every monomial, every variable appears in degree at most 1. For example, permanent is a multilinear polynomial, determinant is multilinear, x squared is not multilinear. So if you restrict your attention to multilinear polynomials, and you also require that the intermediate computations in the circuit are multilinear, okay, so you never go, so you're not allowed to compute non-multilinear monomials that will cancel out, then VP is different than VQP. And determinant gives such an example, and permanent gives such an example. But that's only for the multilinear world. Okay. Yeah.
Determinant isn't in VP.
Yes?
Determinant is in VP. And then we say, but actually it's VQ.
P complete.
VQP complete.
Yes. Yeah, just a reduction is quasi-polynomial. It's not polynomial. Okay, so yeah, so that's variance, and probably you've heard about the famous determinant versus permanent problem. So this is the problem. So you want to give a lower bound on the dimensions. Close the door. So the determinant versus permanent problem is giving a lower bound on the dimensions of a matrix Y such that this is possible. And as we said, to separate or to answer variance extended hypothesis, we need to show a quasi-polynomial lower bound. And what is known today is that the size of Y is at least half n squared. Okay? So something non-trivial, but it's very far from what we want. But yeah, that's complexity theory, right? Okay, great. So that's the prime versus determinant. Okay, now what I want to do next is I want to show the completeness, the VQP completeness of determinant. Yes?
So is there a sense of it will be easier to solve?
Yeah, I don't know. I mean, GF2, I know how to solve it. Other fields, yeah, I have no idea. Okay, good. Great, so what I'm going to do next, I'm going to show the determinant is VQP complete. And for that, we'll introduce somewhat, I mean, okay. So we know that if you have this equality, then the dimension of Y should be at least half n squared. I mean, the size of the matrix. But, I mean, we believe it should be much larger. Right. So the way that you prove that the determinant is VQP complete is basically, I mean, there are several ways of showing it, but what we're going to do is we're going to introduce a new computational model that will also play an important role later. And okay, maybe I'll introduce the model and then speak about things. So the model is called algebraic branching program. Or ABPs for short. And I'm just going to define shortly, it's a model that sits somewhere between formulas and circuits. We know that it can simulate formulas. We know that an ABP can be simulated easily by a circuit. But we don't understand more than that. Okay, so let's define it. So it's going to be an analog of a Boolean branching program, which I don't know if you've seen, so don't worry if you haven't, because I'm going to define it. So an algebraic branching program is a layered graph, an ABP. So it's a layered graph with a single source and a single sink. Okay, and edges go from layer I to the consecutive layer, to layer I plus 1. Okay, so maybe I'll draw an ABP here. So that can be the source. Here we can have a sink. And here we have layers. And edges can go like that. Okay, so it's a layered graph. Layered graph, we have a source, we have a sink, and edges go basically directed from the source towards the sink, and they can only go between consecutive layers. And the edges are labeled with either a variable or a field element. So say you have like x5, minus 7, x2, etc. And okay, so each edge is some label on it, it's a variable. And what is the computation? So basically, you should think about it as some analog of the reachability problem in graph. I mean, if you've seen Boolean branching programs, so what are Boolean branching programs? Right, you just want to check whether there is a path from the source to the sink. So you go over all paths. For all paths, you write the characteristic function of which inputs go over this path, and you do OR over all paths. So here what we are going to have, we are going to have summation over all paths pi from source to sink. Okay, so pi is some paths all directed. Okay, so the paths are directed from the source to the sink. And for each path, we are going to take all the edges in the path and multiply the label of E. Okay, so, yeah. For example, if you have such path, I don't know, x1, x5, x3, x8, minus 7. So you'll have x1 times x5 times x3 times x8 times minus 7. And you will do it for every path, and you will sum all the results together. Okay? So this is the computation of an ABP. And maybe, you know what, let me just do it again. So you can also think about it the following way. Let's say that we look at layer K and layer K plus 1. Then let's call this, put an element here, I don't know, let's call it AKIJ. Okay? So it tells you the label that goes from vertex I here to vertex J here. And let's say that all the size of each layer is at most n. Okay, let's say that there are n vertices in each layer. Okay, and maybe, you know, let's call this V1 up to Vn. Let's call it U1 up to UN. So if you take a minute to think about it, what actually happens here is that we are doing we compute the following computation. We compute the following polynomial. It's like V transpose times the matrix A1 times A2 times A. Let's say we have, I don't know, D layer, D. That's 1, 2 up to D, AD times U. So that's what we compute. Right? It's like a reachability problem in graph, right? I mean, you have a graph, and this just tells you, to each path, it gives a weight, and this is exactly what you get in matrix product, right? Right? If you write the formula, this is exactly that. Okay? So basically, what algebraic branching programs compute, they compute a product of matrices. And what are the entries of those matrices? They are either variables or field elements. Okay, that's what branch programs compute. Okay. It's a they can be the same, but A basically this is like the matrix here corresponds to AK. So AKIJ is what are your AKIJ? Right. Okay. Okay. Great. So, any questions about this representation? So, yes. Yes, that's some extension I'm going to speak about. Yes, very good. Yeah, so what I was about to say is that you can also define several extensions for this model, which does not change much. Maybe I say it here. For example, for projections, instead of just projecting, assigning a variable or a field element, you can also replace yi with a linear function in the xi, or with a low-degree polynomial, or you can even allow more elaborate projections. But basically, the computational, I mean, if you work in the class P, I mean, it's like you can simulate all those stuff. So similarly here, you can, instead of having variables or field elements, you can allow linear functions, you can allow low-degree univariate polynomials, you can allow even labels that can be computed themselves by small arithmetic branching programs, etc. So the model is flexible. This is a basic definition, and up to some polynomial transformations, they captures all those extensions, so you can think about it like that. And in fact, the best way to think about ABPs, I think, is like that. Think about it, you have a product of matrices. That's what you compute. You compute, right, you can even ignore V and U in some sense. You can just say that an ABP takes a bunch of matrices, multiply them, and outputs the 1-1 entry of the product. That's an equivalent definition. So clearly, ABPs capture some linear algebra, right? Because, right, we think about linear algebra as, multiplying matrices, computing determinants, etc. And in fact, in a very strong sense, it captures all of linear algebra. I mean, it's not a formal statement, it's an intuitive statement. But, for example, probably you've heard about it, maybe you haven't seen it, but, if you're given two matrices to multiply them, to compute an inverse of a matrix, or to compute a determinant of the matrix, all those problems are reducible to each other. They have the same time complexity. And similarly, this model computes product of matrices, but it can also compute a determinant. So the determinant is efficient because it can be computed efficiently by an ABP. So you can reduce computation of determinant to a computation of a matrix product. And vice versa. If something can be computed by an ABP that has S nodes, then it can also be computed by a determinant of an S by S matrix, or an S plus 1 by S plus 1. We'll see soon. Okay? So intuitively, you should think about it that the intuition is that ABPs capture linear algebra. So whenever you do linear algebra, in some sense, you're working in the ABP model. Okay, that's one intuition. So for example, so e.g. that as a polysize ABP. Right, so I haven't defined size, etc. So what are the important complexity measures, of course? So we have depth, which is the length, the number of layers, basically. So, yeah, maybe I'll say it here. So ABPs. So depth is the number of layers. Maybe plus 1. Okay, I don't know. Let's not worry about that plus 1, etc. And there's also the width, which is the max size of a layer. So you look at all the layers and you see what's the width of the largest layer. Of course, the number of nodes in the ABP is at most the product of these two things, right? But, okay, so these are the complexity measures. Okay, so I said it captures linear algebra, and that is polysize ABP. And we will also show that if F is computed by size S ABP, then it is a projection of size S or poly S, you know. That. It's actually sizes exactly because I didn't define, you can also define size because number of nodes. And then it will be of size S. Okay, if you have S nodes, then you can represent the polynomial, that polynomial, as a determinant of an S by S matrix in which the entries are either variables or field elements. Okay, and that I'm going to show you next. It can be, it has to be at least a degree. It can be also at most a degree. Yeah, yeah, just parameter that we have. The width is the main complexity measure is usually the width of the ABP. So here's a claim that, or a theorem, is that formulas, I write it somewhat inside ABP. See? Okay, so what do I mean by that? If a polynomial is a size S formula, then it has an ABP of width S plus 1 and depth at most S. And if a polynomial has an ABP of size S, then it has a circuit of size O of S, etc. Right? So everything that can be computed here can be computed here, and everything that can be computed here can be computed here. And we don't know a strict separation between any of those models. As we said, in the multilinear world, we know how to separate those two, and we know how to separate those two. But we don't have a separation here. But we believe it's true. In the monotone world, we know how to separate both. Yeah. At least some people know. Okay, good. So let's show this, and then I'll show that the determinant is complete. Okay. So we want to. So now I want to show the proof of this theorem. Okay. Yeah, proof. So let's start from formulas to ABPs. So formulas. So this is actually very simple because formulas, the nice thing about formulas is that the graph is a tree, right? So you can always do induction on the sides, right? So how does the formula look like? So a formula is either a plus of two subformulas or times of two subformulas, right? Right? That's how a formula looks like, right? The top gate is either a plus or a times. And it's a tree, right? So these two things are completely separated. So by induction, we have an ABP for that side. Let's say the size here is S1 and the size here is S2. So it is the total size. So it's S1 plus S2 plus 2 edges, right? So S equals S1 plus S2 plus 2. So we have an ABP for this and an ABP for that. And now we have to get an ABP for the sum, right? So how does the ABP for the sum look? So let's say that this is for the, let's call it F1, let's call it F2. So let's say that F1 is a certain ABP and F2 is its own ABP, right? Now I have to get an ABP for the sum of F1 and F2. So what do I do? So F1, remember, is the sum of all sync source paths of the product of the labels here and here. So what we do, we just glue these two guys, and then we also glue these two guys. So we identify the source of the two ABPs and the sink of the two ABPs. Now in this new ABP, how does an input-output path look like? So either you go like that, or you go like that, right? You don't have other paths, because except of the source and the sinks, the layers are distinct, right? So if you go here, then you must stay here. If you go down, you must stay down. So when you sum over all paths, you basically sum over all paths that go here, plus all paths that go there. So that's what you do for plus gates. And if you just look at what happens, clearly the size grows most linearly, right? It's like the size of this plus the size of that, we even saved on a couple of vertices. Yes? Yes, exactly. I can just put one up to... Yeah, okay. Yeah, what we said, yeah, that we may have a different number of layers, but... okay, so, right. So we may need to add a vertex, to create a dummy vertex. Yeah, if the depth here is... yeah, thanks, so if the depth here is D2 and the depth here is D1, and say that D1 is smaller than D2, then we may need to add like 1, 1 to create D2. Okay. In that definition, but let's not worry about that. Okay? Yeah, whenever I say something not inaccurate, assume that I said something accurate. Okay? Good. So that's what you do for a plus gate, and now what do you do for a product gate? So again, we have this thing, and now I'll draw it like this. So let's say F1 and that's F2. And the point is that you just glue those things. Right? And now, basically, what will be now, so what happens? You take a path, goes through there, and then it goes with, and then its continuation is any path here. So basically, you just get the product. Right? So that's the reduction, basically. Okay? And and what's the base case? The base case is a variable or a constant. I mean, just do it, okay? So that's the way to reduce a formula to an ABP. Okay, perhaps it's a bit quickly, but I think you get the picture. Okay, great. Now what about ABPs in circuits? So this is, again, it's very simple. Okay, basically what is being computed at the node here? Let's say that we found a way to compute the polynomials at every node here, at level k, and I want to compute the polynomial that are being computed at nodes at level k plus 1. So what is that polynomial here? So let's say the polynomial computed here are f1 to fn, and here we have g1 up to gn. Right, this is the polynomial that's computed here, so it's like we take the paths from the input to that vertex. So basically, if you think about it, you need to take that polynomial, multiply it by, I don't know, n, and this one, and multiply it by a, n1, I guess. Right? So you just have to take the polynomials that you already computed, multiply this one by something, multiply this one by something, this one by something, etc., and then sum them together. So if you just think about it, you get a circuit for each guy here based on the previous layer. Alternatively, you can just take this and write a circuit for matrix product. And that's a very efficient circuit, of course. Right? So it's an exercise to see that you can reduce ABPs to circuits. Okay. So we have until when? Until 11:30? Okay. It's now. No, so it's not good. Okay, so let me... Okay. Okay, so now I want to finish this talk by showing that determinant can compute ABPs. Okay, so what should I do? Okay, so what I want to show you now that, right, so we have an ABP. I want to reducing or projecting ABPs to determinant. Okay, so that's a very nice trick. So what does the determinant compute? Let's think about it, right? Determinant of a matrix, right, is the sum over all, okay, let's write determinant maybe so you remember it. It's a sum over all permutations. Right? That's what it does. So assume that you have a matrix of adjacency, J matrix of a graph. Okay, let's assume what is the adjacency matrix, right? You put 1 between I to j if there's an edge there, and 0 in entry ij if there's no edge. So what is the determinant of this thing? So we have the sigma. Okay, let's the -1 sign. Let's forget about it for a minute. So how does the permutation look like? Right? We know that each permutation is basically a product of cycles. Right? I mean, that's something we learn in discrete math. When you take a permutation elements, it's like a product of cycles. So basically what you do is you cover your vertices with cycles, right? Because you have to cover all elements 1 to n here. Maybe some elements appear, I mean, they're not appearing as their own cycle, etc. I mean, can either cycles of length 1, maybe longer length. For each cycle, you do the cycle, so you multiply all the edges of the cycle, and you do it for each cycle. And at the end, you also introduce the sign, right, of the permutation. So that's what you do. Now, what we are going to do is we are going to take the ABP, and we are going to make a graph out of it so that the only cycles that we will consider will have, I mean, all the cycles will have the same sign. Okay, maybe just do it. It would be simpler if I show it. So let's take an ABP. Okay, so that's the ABP that we have. What we are going to do, we are going to do the following. We are going to add self loops with weight 1 for all internal nodes. So it means without the source, I don't do it for the source or for the sink. So each node here, I'm going to also have 1 like this, etc., but not for to the source and sink. And I also add an edge with, okay, either plus or -1. It depends on the layer. I mean, don't worry about that. Like that. From sink to source. Okay. Well, that's what we do. And now, and let X be the weighted adjacency matrix. What do I mean by weighted? For each at entry ij, if you have a variable, you put the variable. If you have a field element, just put the field element. Okay? And I claim that the determinant of that matrix equals the polynomial that the ABP computes. Okay, so that's a claim that the determinant of this matrix equals the sum of all paths from, I mean, if you ignore those extra edges, etc. The number of nodes. Right? For each node, we have a row and a column. Now, what happened? Because how does a cycle cover look like? What are the only cycles here? So a cycle can be, those are cycles, right? I mean, the self loops. But if you look at that vertex, it sits, I mean, on which cycles does it sit? Every cycle must get here, then go back. Right? So this guy sits only on cycles, and they are this is a directed graph, don't forget it, right? That start from here, go somewhere, maybe they loop some, they go back. So basically, all cycles also have the same length, right? Because you go from this to the first layer, to the second layer, to the third layer, etc. Right? So if you take the determinant and you look at the formula that you get, basically the only cycles that you are going to get are cycles that correspond to paths, and all variables that are not on the path, you are going to have self loops attached to them. The self loops have weight 1. The cycles are of the same length, so they all have the same sign. Right? And we also put the vertices in topological order, right? So, I mean, it's all the signs of the permutations will be 1. And basically that's it, right? because the weight of a cycle is the product of the things on the cycle, and that's exactly the product of the labels on the path. And the self loops don't add anything because they have weight 1. So okay, so it takes, I think, 5 minutes to digest it, and since we have a break, it's a good time to digest it. So yeah, so that's. So maybe before just a second. So what we've seen now, we've seen that formulas reduced to ABPs, ABP reduced to circuits, and everything, any polynomial that is computed by an ABP is also a projection of determinant. And yeah, you know, maybe to finish off the completeness, I'll do it after the break. Just okay. So let's take how long? It's 20 minutes.